record this thing. Yeah. All right. Now, directed graphs are graphs whose edges have an assigned direction. So before, our edges didn't have any arrows. That just means if a vertex is connected to another, then that vertex is connected to this vertex. Now it's different. Now vertices have a direction. If you have an edge from A to B, you might not have an edge from B to A. So connectedness is different in this sense. So now the concept of degree also changes. Now there's an in degree, which is the number of edges that come into a vertex, and the out degree of a vertex, which is the number of edges that come out of a vertex. As you can see on this slide, this vertex has one edge come into it, so it has an in degree of 1, 2 edges coming out of it, so it has an out degree of 2. All right. Okay. And then here's an application of directed graphs, which is your favorite directed graph, the requisite graph of CS majors. And it's directed because you have to take one class before the other. It's like there's an order to it. So yeah. All right. Any questions? Or give me a thumbs up. All right, cool. Okay. How do we implement it? There are two main ways to implement graphs in code. One is adjacency list and the other is adjacency matrix. And as we talked about, adjacency in an adjacency list, it has a list for every single vertex representing the vertices adjacent to that vertex. And for instance, if you have an undirected graph, if 0 is adjacent to 1, then 1 is adjacent to 0. So you would have to add 1 to the list for 0 and add 0 to the list for 1, like so. And of course, you can also represent directed graphs if you just don't add the other direction. So here we add 2 to the list of 0, which we use to represent an edge that goes from 0 to 2. I mean, you can think of it the other way, but it depends on, I guess, your own definition. And for adjacency matrices, it's basically an n by n matrix where a 1 means there's an edge from, I guess, a 1 at position ij means there's an edge from vertex I to vertex j, and a 0 means there's no edge. All right, so here's a directed graph, and do you think you can come up with the adjacency matrix for it? I'll give you a minute. Any ideas? So where should the 1s be? Alright, so there's 1 in the first row and the last column. So that means an edge from 0 to 3, which yes, yeah, there is an edge from 0 to 3. Yeah, the one from this row with 1 on left and 2 on top. Right. 2 to 3, and yeah, and from 3 to 1. Okay. Cool. Yep, that's exactly correct. That's the adjacency matrix representation of this directed graph. Nice. And to see it in code, you just set it to 1, and you're good. Right. And some comparisons between the two. Adjacency lists are pretty space efficient, as opposed to adjacency matrix, who always which you always have to spend in squared space for. But adjacency lists are really slow at checking adjacency of two vertices. If you think about it, you have to go through the entire list before you can be sure that this vertex is adjacent to that. But in adjacency matrices, if you're given two vertices, you can instantly decide whether they're adjacent or not just by looking at that location in the array matrix. Okay. So for example, for this graph, the adjacency list only stores 8 integers, but the adjacency matrix has to store 16, regardless of what the graph looks like. All right, any questions so far? All right, cool. And we will go on to BFS, in which we start at some vertex and then explore all the closest vertices before exploring the further ones. So in an animation, it would look like this. Yeah. It basically ripples out. So yeah. And then as we talked about before, we need to keep track of which vertices we already visited so we don't visit them again. And then we need to figure out which vertices we need to visit next. And then in the BFS order, the best data structure to figure out which vertex we need to visit next is a queue. And here's a reminder of how queues work. You can refer back to it any moment. And here's the pseudocode for BFS. So we first create a queue so we can use it. And then we mark the starting vertex as visited, put it into the queue. So now while the queue is non-empty, you take the vertex out of the queue, and then for all the unvisited neighbors of the, you put it into the queue and mark each neighbor as visited. So since queues are first in, first out, once you take out a vertex from the queue, that's the closest unvisited, or I guess closest unprocessed vertex from where you started. Then its neighbors are next closest unprocessed vertices from where you started. Right. So I guess, and then combine that with the first in, first out order of queues. Maybe you can try to visualize how in this way BFS searches the closest vertices first before the further ones and how it ripples out. And here's a concrete implementation of BFS. Yeah, so it's basically just translating what was on the previous slide. Create a queue at the first vertex and set it to visit. You visit it. While it's not empty, you take the first one out, and then for all of its unvisited neighbors, push it to the queue and set it to visit. Have a question about the code? All right. Then there's DFS, which is quite similar. Except it searches down a path until it can't anymore, and then it backtracks and searches down a different path. And the implementation of DFS is actually really similar to BFS if you decide to use a data structure, because it's the exact same thing except you use a stack instead of a queue. And that's just because of how the order of the two searches work. But, oh, okay, I guess there's a cheat sheet for stacks too. But you can do it much easier with recursion. And I hope you remember how recursions work. It's function calling itself. Like the factorial function right here, which technically doesn't terminate. Should have a base case. All right, so here's the recursive DFS code. So like before, every time you visit a vertex, you set it to be visited. And then for each neighbor that's unvisited, you just recursively call DFS instead of pushing it into a stack. So, because if you think about it, function calls are basically a stack. Right. Does this make sense? All right, and here's a slide that you can read you want to, about this, what use cases BFS and DFS have. And you can gaze at the animations too if you want to. And here's the table comparisons. BFS explores all adjacent vertices, or like the closest vertices first. And yeah, it can be used for shortest path because of that property, because it finds the closest ones first. And then DFS searches as far as possible before backtracking, as I said. And it can be implemented recursive, which is really cool. All right. Now, how do you do shortest path with the DFS? So, I guess if you want to read the slide, it says we can go through all adjacent vertices, giving every adjacent unvisited vertex path length current path plus 1. Does that make sense? Okay. Cool. Yeah, so why does that work? Because every time we reach a vertex in DFS, there's no shorter way to reach that vertex. Otherwise, it is the neighbor of a vertex that's closer from the starting point, which, because of the first in, first out order of queues, would have been popped out of the queue earlier. I hope that explanation made sense. Continue. And to implement this, we can just, in addition to the BFS, keep track of an array or vector called distance. And we can set the distance of the starting vertex to be 0. And then every time we add vertices to the queue, we just add 1 to the distance to the current vertex. Short recap on what the previous slides are talking about. And then we're going to look at connectedness again, which we can implement with both BFS and DFS. What is a connected component again? So a graph is connected, or I guess a connected component is a subset of vertices in a graph such that there exists a path from every vertex to another. It's basically what you think connected means. And if every vertex in a graph are connected, then the graph is called connected. And it's pretty easy to determine whether a graph is connected. You just run BFS or DFS on any of the vertices. And after you finish it, if there are unvisited vertices, then the graph is not connected. Does that make intuitive sense? Do you think you can explain one? Yeah. 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 I guess it's to rephrase it in the contrapositive way, which is usually how people like give intuitive proof for this. If there is an unvisited vertex, then it's not the neighbor of any visited vertex. So it's disconnected. In other words, it's disconnected from whatever you DFS on, which is the set of visited vertices. Which is pretty much, I think, what it says here on the slide. All right. And then an extension for this is that we can, in addition, keep a component ID every time we DFS or BFS. So the algorithm goes like, you first choose a random vertex, you run DFS on it, and then you give all of those vertices the same ID, say 1. And then after that, if there are unvisited vertices, you choose one from those, and then you run another DFS or BFS on them, and then give them an ID of 2. So if you continue this, by the end, you'll have, you would have partitioned your graph into some number of sets of vertices that have different IDs, and they will, and every vertex that has the same number will be in the same connected component. Does that make sense? All right. Here's a quick recap. Use BFS or DFS, and it works on pretty much every graph. And you can turn the visited vector into component ID vector to do what I just said. You can find all the components on their own. All right, that was the end of the review. Now let's go on to some new topics. Trees. All right, so trees usually look like upside down real life trees. That's what they claim. I don't agree. A tree is just this thing that looks like this. And then some examples in real life of trees is like a file system or a coarse requisite graph. Actually, no, that would be a DAG, which we'll talk about later. But choices in a game, like the one on the bottom right corner. If you have a tic-tac-toe game, like if you have an empty board, you might have 9 choices. Here we show 3. And for each of those choices, you might have more choices for the next player. And then for each of those choices, you have more after that. And then this is a tree. And then another thing about trees is that if it has n vertices, it always has n-1 edges. Now let's some terminology of trees. Here we are using a rooted tree, which you'll understand what it means very soon. So a node is just anything in a tree, like this one. And a root node is the only node in the tree with no parents. So the one on the top is here we denote as the root node. So a rooted tree is a tree with a root node. And a parent is just a node pointing to the node you're interested in. So if this were n, then this is the parent of n. And an ancestor of n is the parent of n, or the parent of n, or the parent of an ancestor of n. So all of these are ancestors of n. Similarly, child is just what n points to. Descendants are either the child of n or child of a descendant of n. So these are all the descendants of n. And then there's also the concept of leaf node, which is any node with no children. So all of these are the leaf nodes of this rooted tree. Now let's see an example of trees in comparative programming, I guess. And if you want to look at the problem on Caddis, you can click on that link. Give you a minute to read. Okay. Do you have any thoughts for this problem? I mean, the problem statement is very confusing in my opinion. Right, you can't. So if you actually just generate the tree in, I guess, the way you described, it would look like this. And yeah, if you look at the graph, there's really only one way to reach 25 or 14. And yeah, if you do a DFS on the tree, you will get exactly the path down to the root. So that was great. But here we have like a different solution. So there's some starter code if we wanted to like actually solve it, but there's our solution, which is a lot more stupid than a DFS. It's just going through every single edge in the tree every time and finding the next possible node to go to. Because if you look at the tree again, there's only one place you can go from every node. So yeah, it's basically looping through all of input every time and then finding the only place you can get to. And then eventually you're gonna get to the root. Guaranteed by the problem. Does that make sense? Yeah. Might be more intuitive to just run a DFS if you know how to do it. Yeah. Then let's go on to DAGs, which stand for directed acyclic graphs. As you can probably tell from what it's the name, it's a directed graph with no cycles. So can you identify which of these are DAGs? You're correct. It's just the first one. And here's the cycle. Here's the cycle. So yeah, this one doesn't have a cycle. So that's the only DAG. So what can we do with the DAG? Just first of all directed trees are DAGs because trees don't have cycles in them. So if they're directed, they would be directed acyclic graphs. Okay, some real life examples of DAGs are program build dependencies. If you've ever dealt with make or CMake, you probably know what that is. And course prerequisite charts are also DAGs because you can't have a cyclic prerequisite, otherwise you won't be able to graduate. You have to do, I don't know, CS33 before CS32, but you have to do CS32 before CS33. Yikes. Okay. And because DAGs are directed and do not contain any cycles, they can be topologically sorted. And to talk about topological sort, we need to first define topological order. So if you read the slides, it says that topological sorting of vertices of a DAG is an ordering of the vertices such that if there's an edge from I to J, then I has to come before J. That might be a little bit confusing, but if you look at this graph here, every edge, okay, so every vertex that has an edge pointing to another vertex has to come before that vertex. So as you can see, all the arrows here point to the right. So that means this is a valid topological ordering of this graph. And you might want to note that topological orderings are not always unique. For example, you think about it, if you swap the places of B and C, it doesn't break the topological order. Can you see that? you switch B and C, it's still a valid topological ordering. Yeah. But if you swap A and D, then A would be pointing to D, but coming after D. So that would be not good. All right, then let's see how we do topological sort. So here we have a directed tree, which we said we claim to be a DAG. Let's see how we can come up with the topological ordering of this tree. Okay, so if you think about it, if we start from the root, we want to have everything it's pointing to come after it. Or I guess in this case, we're doing a reverse topological sort. So we want everything it's pointing to come before it. Then we probably want to look at what it's pointing to. The same thing there. And since one doesn't point to anything, we can safely put it at the very beginning of our order. Now I want to switch back to Zoom to see what I'm doing. Right. Yeah. So now we go back to 3. It still points to something we haven't processed yet. So it's 6. 6 points to 4 and 7. So since they don't point to anything else, we can safely put that in front of our reverse topological order. And then now 6 doesn't have anything it's pointing to that's not been processed yet. So we can now put 6 in order. And the same thing follows. So now if you, I guess, read this ordering from right to left, everything that comes after everything else is pointed to. That was not a good explanation, but if something comes after something, then the second something, wait, I'm really bad at explaining this, but I'm sure you know what topological orderings are. Do you think you can explain it? Heap sort. Can you explain that? Why does that remind you of heap sort? That's a very interesting parallel that I've never thought about, but let's see. Well, the example is like a binary search tree, but I think that the relation you found between this and heap sort is very interesting, but I have to think about it more to see if there's any significance in there. But Topsort is, in my knowledge, very different from heap sort. Well, heap sort is sorting a sequence of numbers, or a sequence of comparable items, and Topsort is giving you, it gives you a topological ordering of the nodes in a graph or in a DAG. So yeah, I guess in some mathematical sense, it's like giving you an order of a partially ordered set, such that it doesn't violate the order. That's something math major would say, but okay. Let's get back to the definitions. So if I comes before j, actually no, if there's an edge from I to j, then I comes before j. I guess what we're about to do an example on this, but the real life application that might be intuitive to you is course prerequisites, as you said, is a DAG. So if there's an edge from I to j, that's like if I is a prerequisite of j, you have to take I first before you take j, right? So if you think about it, topological ordering on a prerequisite graph gives you an order of the classes you can take. such that you don't violate any prerequisites. Does that make a bit more sense? So the main idea is, as we just walk through the animation, you start on whichever node you want to start on, usually the root. And you perform DFS on the node, but at the end, you add the node to the topological order. And then that gives us the reverse topological ordering of the graph. So yeah. I guess we can walk through the animation again. If you look at it closely, it's actually just a DFS traversal of the graph. So 8 goes to 3 is 1. And then we look at the other unvisited vertex. Do the same thing. You see how that is a DFS? Where might we see this in real life? We set course requisite graph. And let's do this example problem of top sorting the CS course graph. Is there a natural order on the graph? And is there an order to take the CS classes so that you don't violate any prerequisites? You have a class you want to take. What classes do you have to take first, and in what order? And so before doing all these, we need to first somehow represent each class in our program as a node in the graph. So we have to use a map the name of the class to our representation of the node. So do you know what a map is? Okay, cool. What I like to think is that a map is just an array that uses objects as indices instead of numbers, because C++ has a really nice syntactic sugar for it. Yeah. Okay. This basically repeats what we just talked about. Is how topological sort works. We DFS, and at the end, we add it to the list. Okay, so if we have this sample input, which says we have 5 classes. First one being CS31, which has no prerequisites. Next one being CS32, which requires CS31, and so on. And then at the end, we want to take CS111. So in what order should we take the classes so that we don't violate any prerequisites? Yeah, that's right. You have to take 31 first, and then you have to take 32. Then you can take either 33 or 35L in any order, and at the very end you can take one of them. But our job is to generalize this process using code. So if you want to implement it, you would use this starter code. But yeah. So I guess I'm assuming you're not in a mood of typing code right now. Or you can do it if you want. Okay. So I'll just walk through the code. This is just for parsing the input because it doesn't tell you how many things are on the line. So you have to do some shenanigans to parse it, but that's not the most important part in this. Most important part being this line, which is essentially the whole top sort we have implemented here. As we have described before, it's a DFS where you do the usual, you set whatever you're visiting to true to visit it, and then for each unvisited neighbor, you run the same BFS on it, and when you get to the end, you push the thing into the list. And that'll give you a reverse order. But in this case, because of how our edges are oriented, because our edges go from the course to its prereqs, we want to reverse topological order. So if you're pointing to that thing, then that thing has to come before you. So that's like the opposite of what we define topological ordering as. So here, if we get a reverse ordering, we actually get the actual answer. Does that make sense? Okay. So if we run our program on this input, we get this output, which is one of the two valid topological orderings that we can take. All right. And then if you want to look at this problem, it's pretty much the exact same thing, except you change 2 lines of code. Do you want to take a look at it? No. Do you have any ideas for it? Or, as I said, you changed 2 lines of code from the example problem we talked about. Can you figure out what's the difference between this problem and that problem?
It's fine if we can't figure it out, because I guess you really have to like implement the problem or implement the problem to see what the difference is. If you look closely, the way they want you to output the solution is in a different order than how we output this solution for taking classes. And then you also have to switch the directions in which you read in the graph to, I guess, conform to what they want. So I guess these are the details you have to pay attention to when you actually implement the problem instead of, I guess, solving a hypothetical problem. Let's go on to the next topic about cycle detection, which we will do using DFS. We call that a cycle is just the special case of a path where it starts and ends on the same vertex. And how would we detect a cycle? If you just naively think that every time you see a visited vertex, you found a cycle, that might not be correct. So suppose you're doing DFS and you reached a vertex that's already visited and you think it's a cycle, but it could be that it was visited from, so say you have a node that's pointed to by two different vertices. You visited it from one of the vertex and now you visit it again. Even though you visit a visited vertex, it doesn't form a cycle. It's just like a fork, or yeah, it's just a fork, right? So how will we actually find cycles using DFS? So instead of using a single notion called visited, we use both visited and good. So here by good, we mean that we've processed every single vertex that's reachable from this vertex, and there are no cycles. So if we ever reach a good vertex, we know we're done on that end. because from that vertex on, there are no cycles. So how do we find cycles? We have another indicator called visited, which specifies which vertices have been visited in the current DFS call. Okay, what does that? So, DFS finds the deepest node before it backtracks, right? So once you start backtracking, we just remove those vertices from our visited this DFS call list. So if you think about it, only if you get to a vertex that's visited this DFS call will you have a cycle. Just for an example run through or walk through this. If we choose to start our DFS on this node, we call this visited. And then we do the usual, the DFS. We go to this node, and this node has no more neighbors or no more unvisited neighbors, so we call it good. And then we find the next neighbor, and then keep DFSing down that path first, I guess. And then we got here, there's nowhere to go, so we call this good. And then this will become good too. And we go to the next unvisited neighbor. That's good. And now that's good. Because all of its neighbors are good. But then because if you think about it, we were at this node, we went down here, it was good. We went down here, it was good. So we should check this. But this was, quote unquote, visited this DFS call. So now we found a cycle. And to implement that, it's pretty simple. It's almost the same as before, except we use 2 Boolean vectors to keep track of both visited and good. So yeah. If we get to a visited node, we return false. That means there is a cycle. If we found a good node, we return true. That means there are no cycles. And then we set it to visited, and then for each, well, it should be unvisited. Okay, for each neighbor. If it returns false, that means we found a cycle. So we return false immediately. Otherwise, we would return true at the end. Yeah. And here's a short recap. And then here's an example problem for cycle detection. You want to go ahead and read from the same. Have any ideas? So you said to read the graph or read the input as a directed graph where the first number points to the second. So yeah, so you can first run the cycle detection DFS on, you said, a node with no parents. That would work, but I think you can actually run it on any. Actually, yeah, I think any node would work because if you think about it, every node in a cycle has a parent. So, yeah. And then you would do topological sort on it, and then since you read it as if A is on top of B, then A points to B, and you would want the reverse topological order if you decide to read in the input that way. Yeah, that's great. And do you have any questions? If you have a cycle, then the node in the cycle must have parents. And if you want further reading on this, I would suggest you look up Kahn's algorithm, which is what I personally use for topological sort. And then, yeah, and then if you use Kahn's algorithm, it basically does the topological sort in the correct order, not like in this algorithm where it does the reverse and then reverses it. In Kahn's algorithm, you do it the correct order, and at the end, you would remove all the edges from the graph if it were a DAG. And if there are cycles, that is, so if it's not a DAG, there will be cycles, right? Then there will be leftover edges. And that's how you would detect cycles using Kahn's algorithm, while at the same time doing Topsort. So if you're interested in reading that, yeah, feel free to search it out. And you're welcome to do the contest, because I think we really start to appreciate the algorithm and the details in the implementation and write the code. Thank you. I would just conclude my presentation. Right? You want to do a contest with me?